Hello everyone. This is the continuation of the Cauchy problem for the wave equation. Here we are going to prove a theorem regarding Cauchy problem of wave equation. The statement of the theorem is fix capital T which is greater than 0. The Cauchy problem utt minus c square into uxx equal to 0 for minus infinity less than x less than infinity and 0 less than or equal to t less than or equal to capital T. With the initial conditions u of x0 equal to f of x and ut x0 equal to g of x for minus infinity less than x less than infinity is well posed. This Cauchy problem is well posed for f belongs to C2R and G belongs to C dash of R. That is in the domain 0 less than x less than minus infinity less than x less than infinity and 0 less than or equal to t less than or equal to capital T. Okay, so if we fix capital T which is positive, the Cauchy problem this for this interval, that's minus infinity less than x less than infinity, 0 less than or equal to t less than or equal to capital T. For this domain, this Cauchy problem is well posed for f belongs to C2R and G belongs to C dash R. We know the well posedness of the solution. A problem is said to be well posed if the solution exists, and second one is the solution is unique, and third one is solution is stable or stability of the solution. That means stability means a small change in the condition give rise to a small change in the solution. Okay, so that is well posed. A problem, we already discussed that a problem is well posed if solution exists. Second condition is solution is unique, and third condition is stability. Stability means a small change in the initial condition gives rise to a small change in the solution. Okay, so we have to prove that if the domain is actually generally our domain for Cauchy problem was minus infinity less than x less than infinity and t greater than 0. So for t greater than or equal to 0 or t greater than 0. So here the domain is 0 less than or equal to t less than or equal to capital T. So that is the time t restricted from 0 to capital T. So in that case, if f belongs to C2R and G belongs to C dash R, then this Cauchy problem in this domain minus infinity less than x less than infinity, 0 less than or equal to t less than or equal to capital T is well posed. That means we have to prove that the solution exists, solution is unique, and the solution is stable. Okay, so proof. Actually, the existence and uniqueness. The first existence and uniqueness of the solution is directly follows from the D'Alembert's formula. We have the D'Alembert's formula is actually gives a solution for the Cauchy problem, and we already shown that any solution of the Cauchy problem is necessarily equal to the D'Alembert's solution or D'Alembert's formula or D'Alembert's solution. Okay, so we can say that the existence and uniqueness of the solution is directly follows from the DLMS solution. So the existence and uniqueness of the solution is directly follows from the DLMS formula. So DLMS formula provides a solution for the Cauchy problem, and we have shown that any solution of the Cauchy problem is necessarily equal to the DLMS solution. Okay, so we already discussed the DLMS solution. So we already shown that uh, any solution of the Cauchy problem is nothing but is equal to the DLMS solution. Okay, so the existence part and the uniqueness part is over. So we will directly follow from the DLMS formula. The solution is exist and is unique. Okay, now if F belongs to C2R and G belongs to C dash of R, then we have U belongs to C2 of R cross 0 infinity intersection C1 of or C dash of R cross 0 infinity. Okay. Therefore, the DLMS solution is a classical solution. Therefore, DLMS solution is a classical solution. On the other hand, if f belongs to C of R and G is locally integrable, then the DLMS solution is a generalized solution. Okay. On the other hand, for f belongs to C of R and for G that is locally integrable, the DLMS solution is a generalized solution. Okay. Now we have to prove that the stability. We have to prove the stability of the problem. So to prove the stability of the problem, we have to show that a small changes in the uh, condition, a small changes in the initial condition give rise to a small change in the solution U. Okay, and that is the stability of the problem. Okay. Now to prove the stability of the problem, we need to show that small changes in the initial condition give rise to small changes in the solution. So our initial conditions are f of x and g of x. So we have to show that for small changes in the initial conditions f and g, uh, we have a small change in this solution u. Okay, so let ui be two solutions of the Cauchy problem with initial conditions fi comma gi for I equal to 1 comma 2. That means our Cauchy problem is this actually. So u1 is actually for uh, if we have two initial conditions. One is for f1 and uh, f1 g1, another is f2 g2. So for f1 g1, that is utt minus e square uxx equals 0, minus infinity less than x less than infinity, 0 less than or equal to t less than or equal to capital T, with u of x0 equal to f1x, ut of x0 equal to g on x. That is the one problem, and we are supposed that u1 is the corresponding solution of that problem. In the second problem, we changed this initial condition for f2 and g2. Okay, if the initial conditions are f2 and g2, then let the solution be u2. Okay, then that is the cases we wrote here. Now therefore the solutions are given by, therefore u1 x comma t is nothing but 1 by 2 into uh, f1 of x plus ct plus f1 of x minus ct plus 1 by 2c into x minus ct to x plus ct g1 of s ds, and u2 of xt is nothing but 1 by 2 into f2. This is with f2 and g2. So f2 of x plus ct plus f2 of x minus ct plus 1 by 2c into integral x minus ct to x plus ct g2 of s ds. So these are u1 and u2. Okay, now if uh, consider as small changes in the initial conditions fi and gi. Okay, so if mod f1x minus f2x is less than delta and mod g1x minus g2x is less than delta for all x belongs to R. That is, we are considering a small changes in the initial conditions fi and f and g. Okay, now then for all x belongs to R and 0 less than or equal to x less than or equal to capital T, we have, what about mod u1 minus u2? We need to prove that for this small changes in f and g, there will be a small change in u. That is what is we need to prove. Okay, so small modulus of u1 minus u2 is nothing but modulus of this minus this, that is equal to modulus of this 1 by 2 into this plus this. So 1 by 2 f1 x plus ct plus f1 x minus ct plus 1 by 2c into integral x minus ct to x plus ct g1 s ds minus u2 is nothing but 1 by 2 into uh, f2 of x plus ct plus f2 of x minus ct minus 1 by 2c into integral x minus ct to x plus ct g of s ds. It's modulus of this. Now this is nothing but we can write this as less than or equal to 1 by 2 into f1 of x plus ct. This can be written as 1 by 2 into f1 x plus ct minus f2 x plus ct. So we can write like this. 1 by 2 into modulus of f1 of x plus ct minus f2 of x plus ct plus 1 by 2 into modulus of f1 minus f2 or f1 of x minus ct minus f2 of x minus ct f1 of x minus ct minus f2 of x minus ct plus 1 by 2c into this minus this. So modulus of integral x minus ct to x plus ct g1s minus g2s ds. Okay, because we have modulus of a plus b is less than or equal to modulus of a plus modulus of b. So uh, this is a b c. Okay, so now this can be written as actually 1 by 2 into f1 of x plus ct minus f2 of x plus ct here, and here is 1 by 2 into f1 of x minus ct minus f2 of x minus ct. So this is, we know that the modulus of the integral is less than or equal to, we can write this is integral of the modulus. Okay, so here we can write 1 by 2 modulus of this. Actually we can replace this by, or we can write like this, f1 of x plus ct minus f2 of x plus ct plus 1 by 2 into modulus of f1 of x minus ct minus f2 of x minus ct plus 1 by 2c into integral of x minus ct plus x plus into x plus ct modulus of g1s minus g2s ds. Okay, so this is less than 1 by 2 into, we have the f1x minus f2x is less than delta. We have assumed that f1 minus f2 is less than delta, and modulus of g1 minus g2 is also less than delta. So we can write like this, 1 by 2 into, this is f1 of x plus t minus f2 of x plus t is less than delta. So plus 1 by 2 into this also less than delta plus 1 by 2c into integral x minus ct to x plus ct, this is also less than delta ds. So this is equal to, this is 1 by 2 delta plus 1 by 2 delta, which is delta plus 1 by 2 c into delta. Integral of this is nothing but x plus ct minus x minus ct. Okay, so this is equal to delta plus 1 by 2c into delta. This is actually 2ct. So this is delta plus delta t. But we know that 0 less than or equal to t less than or equal to capital T. So we can write like this. This less than or equal to delta plus delta capital T. That is 1 plus t into delta. Okay. So this is mod u1 minus u2. Mod u1 of xt minus u2 of xt is nothing but which is less than or equal to, which is less than, right? So here we have less than, so this is less than this. Okay, so we have obtained when mod f1 minus f2 is less than delta and g1 minus g2 is less than delta, implies mod u1 minus u2 is less than 1 plus t into delta. Okay, so therefore for a given epsilon, greater than 0, we can take delta which is less than epsilon plus 1 plus t. Therefore we have for every x belongs to R and 0 less than or equal to t less than or equal to capital T, we have what, modulus of f1 x minus f2 of x less than delta and g1 of x minus g2 of x less than delta, implies mod u1 xt minus u2 xt is less than 1 plus t into epsilon delta, that is less than epsilon. Okay, so for every epsilon greater than 0 we have delta which is less than epsilon by 1 plus t, such that a small change in f and g implies a small change in u. Okay, that is the problem is stable. That is the stability of the problem. Okay, hence the proof. Now we have a remark. Actually, here actually we changed we fixed our t. That is, we restricted our time t to up to t only, capital T. Okay, and in that case, if f is belongs to C2R and g belongs to C dash R, then we have the Cauchy. We have proved that this Cauchy problem is well posed. That is, the solution is exist and solution is unique, and it is the problem is stable. Okay, if one or more of these properties is does not hold, then we can say that this solution is ill posed. Ill posed. Okay, the problem is said to be ill posed if one or more conditions of this uh, violated. Okay, now we have the remark one. The Cauchy problem is ill posed on the domain minus infinity less than x less than infinity and t greater than or equal to 0. That means here the condition is actually t greater than or equal to 0. This is our general sort condition. So here the restriction is not there for t. That is, in that case we cannot prove this. Okay, this proof is by the stability we cannot prove. The stability is by 0 less than or equal to t less than or equal to capital T. That is what is we obtained this delta plus delta into t. Okay, so in that case the stability cannot be proved. So the Cauchy problem is in that case ill posed. Okay, now the remark 2, the D'Alembert's formula is also valid for minus infinity less than x less than infinity and t less than or equal to t less than or equal to 0. That is for negativity. Okay, and from capital T to 0. So the elements formula is also valid for this in the domain, and the Cauchy problem is also well posed. Well posed in this domain. Okay.